Okay, the first speaker in this last session of today is Fernando Quevedo, and he will tell us about de Sitter versus quintessence in string compactifications.
Okay, well, thank you, Bert. Well, I joined the other speakers to thank all the organizers for putting together this nice workshop. And it's always a pleasure to come back to Madrid. This is one of my favorite places, and it's great to see your friends here all the time. So this work is based in this collaboration, a paper that came out a few weeks ago with Michele Ciccoli, Shanta De Albuis, Anshul Maharana, Francisco Moya, and myself. And this is exactly the same title. So I will just base my talk on that paper, and of course I will refer to details for that paper because the paper is long, and then I can just cover a small amount of it. So the outline is more or less as follows. This is I will just describe a little bit the sitter, although several people have mentioned already. Then quintessence, then the sitter versus quintessence, then the sitter and quintessence, and then not the sitter and non-quintessence. Okay. So essentially, this one I will say very few, but just to give you info. And this, the sitter and quintessence, that shows that I am a diplomat. So and we'll see, I'll try to go through it in the... So let me just quickly review, very quickly, this Moduli Stabilisation in type 2B, following the GKP, KKLT scenario, and then the large volume, LVS. So we have the moduli, the dilaton, the Kahler moduli, and the complex structure moduli, the standard four-dimensional effective potential with the three-level flux superpotential, the Gukov-Witten superpotential. And it happens to be on the Kahler structure part, on the Kahler moduli part, the no-scale condition is very crucial, so it satisfies this condition. And that means that even that the superpotential doesn't depend on the T fields, only depend on U and S, the complex structure and dilaton, then the scalar potential now is positive definite because of this cancellation, and then you stabilize the U and the S fields in a supersymmetric way to dw equal to 0. But yet, T is still arbitrary. That's only tree level, and of course there will be quantum corrections, alpha prime and loop corrections to that, and we can just estimate how the scalar potential will change, because the potential will be 0 at the minimum, and for any value of the T field will still be 0, and the delta V will be proportional to delta K and delta W, the Kahler potential and the superpotential, with these coefficients. And so there are three options, three ways to go. One is that the standard one, where W0 is bigger than delta W, because just usually delta W is a small perturbation, and the delta K bigger than delta W, because W only gets non-perturbative corrections, which are usually suppressed compared to perturbative corrections. So once this is satisfied, which is the generic case, then you get a runaway behavior. That's the standard Dine-Sauber problem that has been haunting us for 30 years or so. The novelty of KKLT and then LVS is that by using this flux superpotential, there are two ways to get around this. One is that using the freedom of the fluxes, which gives us a lot of freedom of values of the superpotential, you can tune the superpotential W0 to be of the order of delta W, which is non-perturbative. So that means that W0, you tune the fluxes, which is very complicated because you're tuning, say, 10 to the many integers to get something which is very small. But that's a big assumption. Once you do that, then you can find this term is still negligible. This term will compete with the next order term, the delta W square, because now W0 delta W will be a further delta W square. And then that competition gives you a minimum, and that's the KKLT minimum. Essentially, that's roughly. The other option, the other possibility is when these two terms compete with each other. Usually this is very dangerous because people say you have two perturbative corrections competing with each other, you break perturbation theory. But that's the other point of type 2B, or in general string theory, that can be used in the fact that these two expansions are completely different because there are many expansion parameters, not only the T fields. There are many T fields, so one can be the overall volume, and the other one can be a small cycle. So in that sense, delta K will go like 1 over the volume, but delta W can go like e to the minus a tau. In KKLT, both tau and volume are the same, so this cannot compete with each other. But the generic case is that you have many moduli, so this will be a blow-up mode, and this is the overall volume, so then they can compete with each other. And automatically that tells you that volume is exponentially big, exponentially large, because proportional to volume is e to a tau, and tau is bigger than 1 because proportional to the 1 over the string scale, the string coupling. So that's the LVS scenario. So we have these three possibilities, and that's what people have been building up in the last 15 years or so. The effective theory, people start with the Kahler potential, the superpotential, this is a flux superpotential, and then in KKLT, the scalar potential takes this form, and in LVS, it takes this form. This is the original term I told you about the complex structure and the dilaton part that goes like 1 over volume square, which is important because there is an e to the k in front of everything. The 1 over volume square tells you that this is in scales of the order of the string scale to the 4. Because 1 over volume square times m plan to the 4 is 1 string scale to 4. And this one is scaled like 1 over volume cube, so this is parametrically smaller than that. And that's the minimum. So that's what people have been doing over the years. And again, I want to emphasize there are several Kahler moduli. The overall volume, there's the blow-up modes, which are small cycles that can contract to 0, like del Pezzo surfaces. And then there are other ones called fiber moduli, for which locally it is the manifold is a product of two of the moduli. And each of them comes with many actions, and that will play an important role for us. Each of these modulus has an action partner, and there are many moduli, so there are many actions. Okay, so the sitter, to get the sitter, people try since the beginning many ways, and the original one was anti-D3 brains that has been discussed a lot in this conference. But then there are other proposals. You take the effective field theory, you take the D and F terms in effective field theory, or using what people call T-brains, or using the complex structure and dilaton uplift that I think Team Ras and collaborators have discussed recently, for which DUW and DSW are not exactly 0, but they can give you something different from 0 that can compete with the rest. But there are many other proposals that people came out in the past: non-critical strings, negative coverage compactifications, Kahler uplift, non-perturbative effect on D3 brains, etc. So there are many potential proposals for getting this uplift, and the most popular still is the anti-D3 brain, but we have to discuss all of them. For instance, we'll go quickly with the T-brains. Is essentially a combination of F and D terms, for which either you have a Fayet-Leopoulos, when you plus the F terms, give you a kind of soft terms for the fields, and as long as the field is non-tachyonic, this term is positive, and when you substitute the minimum, this gives you an uplift term. We usually try to avoid using the word uplift because the whole model comes together. It's not that you go first the anti-sitter and do the sitter, but you consider the whole model with the open and closed string moduli, and then find the minimum, and that can give you the sitter or not. In this case, contrary to the anti-brains, the volume, this delta is a number, it's not variation. Delta is a number here. The volume to the 1/3 has to compete with the log of the volume over W0. So for W0 not too different from 1, in order to get a minimum, these two things have to compete, so the volume is large, but not too large. And this has a nice T-brains interpretation, in terms of that once you have fluxes, this equation tells you that you cannot have the wave of the corresponding D7 brain field, the commutator that cannot be just 0, so then you have this triangular form that gives you the kind of boundary state called the D7 brain, the T-brain, and that corresponds to that. This was one of the examples of giving you the sitter. So let me summarize the advantages. The fluxes are, once you have fluxes, that's a complicated thing because it changes your whole manifold. It can be something that you don't know, and that happens to most of the other string theories. But in type 2b, it happens to be a Calabi-Yau, which is warped. So in that sense, you still have control as much as you have control the Calabi-Yau. There's no scale structure tell you that you can have separate stages to do the model stabilization. And then the scales, you have the Gravitino mass, which is the low energy scale, is smaller than the string scale and is much smaller than the Planck scale. So you have a hierarchy that you have things under control. there are two sets of 3 fluxes. That sounds like trivial, but they fix the 3 cycles, but only one may be enough to fix the 3 cycles, but you have 2, and because of that, that would give you a lot of freedom, and that's what the thing that allows you to tuning. The GVW superpotential is not normalized. This is not trivial because usually normalization theorems are there because the superpotential doesn't depend on the expansion parameters. Here, the superpotential, because of fluxes, depends on the dilaton. However, is still not normalized. So you have control on that. And then over the years, several people in the audience and other people have computed the correction, G-string correction and alpha prime corrections to K, and they have been computed and essentially keep all the structure I told you before still holding. That's not trivial. And the Kahler moduli happen to be the couplings in the 7 brains that happen to then, that's the natural thing to fix with the non-perturbative effects. So several things happen in type 2B that makes it ideal to do this work, but nothing, I mean, in principle, fundamentally should be done in the other cases. So the achievements, several, so we have a well-defined prescription that gives you, includes all the ingredients of the string theory that give you brains, orientifolds, warping, etc., that give you this minima. As I said, just 2B with fluxes still give you the Calabi-Yau, so moduli space is understood. W0 smaller than 1 is plausible. It's not achieved yet, something that you have to keep in mind, because for that you need many moduli, many of the complex structure moduli, and the technology has not been developed yet to consider so many equations for those fields. And the perturbative effects that can be affecting the large volume case, they have been over the years in better control because people have been doing the calculations and they keep the structure the same. And as mentioned before, the anti-brain got a little bit of at least from my point of view, it was interesting that once you define this new approach using a nilpotent superfield that adds an extra terms to the superpotential and the Kahler potential, and that makes the anti-brain, you can treat it in a supersymmetric way and in the effective field theory. So that gives it, from my point of view, from the effective field theory, much more robust, the picture. And as I say, there are hierarchies, the low energy scale compared to the Cadusa-Klein and the string scale, and the gravitational mass compared to the Planck scale and to the Cadusa-Klein scale are very small. But there are potential problems to each of the things that I consider. Some people complain about using effective field theory. Some people complain about using the fluxes, in particular the ones that break supersymmetry. Some people complain that there may be other perturbative effects that we may not have computed. And non-perturbative effects, we don't have the coefficients of the non-perturbative effects, usually are not under control, or people cannot compute them. And of course, the uplifting, the way to get uplift, as you have heard, there are several criticisms. And so I see concrete challenges for the sitter. One is, as was mentioned before, define properly the sitter in terms of the S metrics and so on. Seeing it as a metastable state, as a resonance, is a good way to think about it, but it still needs to be more work on it. There are these classical no-go theorems. As I think it's only classical, but it still is interesting to consider them. And then there's this issue that not DS solution of string theory is on the full calculation and control, KKLT, LVS, for the reasons I told you. I want to emphasize not being on the full control means that there's no control at all. I mean, things are being developed and progress has been made, and I think that these are. So it's okay. So then there is a challenges to KKLT and LVS. I think as you referred to this talk by Danielson and Van Riet. So the fluxes under control only in the SUSY 10D. For that we have several discussions, in particular with Sav Sethi. I think that as long as the volume is large and the superpotential is relatively small, his criticisms are not that relevant, but I think something to settle better. the question is how to show the effective field theory. If the tuning of W0, how can you do it explicitly? The high occurrences to LVS, the anti-branes, and so on. So for that, I cannot dedicate too much time because how much time do I have?
Halfway.
Good. Because, but I encourage you to read our paper where we go one by one and then address the pros and cons of each of them. So that was a good opportunity for us to go. One example, for instance, there was a criticism for W0 had to be bound by this. Bounds on W0 that had to be W0 volume to the 1/3 has to be smaller than 1 because of the naive derivative expansion. That would be very bad because for the large volume would be that the volume would be smaller than 1 over W0, which is supposed to be W0 for the 1 for the large volume. However, and you do the calculation correctly, there is an extra coupling here, and once you do that, the bound is more natural. W0 is smaller than volume to the 1/3 positive, and then that is satisfied. So several of these things have been done in the past, and that gives us that encourages that the whole procedure, the whole approach to the whole scenarios are under better and better control. So these are the open questions. One thing that I always like to emphasize is that it's good to get the sitter, but it doesn't matter if you get the sitter and you don't have the standard model, because the sitter is justified by getting, because of dark energy or so, but the standard model we live in here is totally absurd. So getting something phenomenologically, but at the same time doing all this is a big challenge. And the other big challenge is to actually use these things for proper use, for instance, for the cosmological constant, is to populate the landscape. The large number of U moduli plus the vacuum transitions and the standard vacuum transitions, as it was mentioned before, is a big challenge. And I consider that probably the less control part of the whole picture. So this is like a partly full, partly empty picture. So what Thomas mentioned in the previous talk, I think is the partly empty. And I would like to mention that this is partly full. It's partly full. So, and someone has an answer to this puzzle that says it's not up to the observer, but if it was full and you empty it a little bit, it's partly empty. But if it was empty and you fill it a little bit, it's partly full. So I claim it's partly full because we have been making progress. So the picture that we have now compared to the picture that we had 15 years ago, in 2000, is much more better. So you have been building up. And after Thomas' talk, we took a bet now for a bottle of wine for which side we both bet. So at least I have now all the witnesses here. So unfortunately, we may not be alive to check the bet. Okay, so that was the sitter. So now quintessence. So as you have heard in this first, there are all these conjectures, which I find them very, very interesting because that makes a separation, what kind of thing we can say for quantum gravity, in particular for string theory, that is not just captured by just a simple effective field theory without worrying about the ultraviolet completion. So I think this is a very fruitful exercise, and I think we will learn a lot out of this. And the one that I will be referring to is the one that has been mentioned already in several talks, is the one that Kunrun and collaborators came out against the sitter. And that will imply somehow that quintessence is not the sitter, and also hard to get inflation. So then, following the same criteria that we followed for the get the sitter, we can ask how difficult it is to get this, say, in effective field theory, but also in string theory in general. So there have been several challenges that were mentioned also before. The Higgs potential is a concrete way because you have the maximum of the Higgs potential, and that what Arthur and collaborators, and I think Arthur will mention more on that. The point by Joe Conlon about having, if the potential goes to 0 from above, you have to have a minimum. Even if the minimum is supersymmetric de Sitter, you have to pass through the maximum, and others. So, but then of course, all of them, this one and other potential things can be addressed if you modify the conjecture by allowing saddle points. In that sense, that's also has been mentioned before. But that's good to keep in mind. For the Higgs, let me just say a few words. You can identify here, you have the potential for the Higgs and the quintessence field, and then you try to see how around the maximum when h equal to 0, you have to compare V phi compared to V, and then it comes out that V gives you something which is very big, which is order of TeV, and then V phi has to be bigger than that, so it's very complicated to get, so you have to do, it fails by 10 to the 50 something orders of magnitude. I present the blackboard because we got very angry that we had this equation written in the blackboard, and then the next day Arthur and collaborators scooped us, so, so we didn't publish the paper. But that was the proof for that, and actually my collaborator sent it to his girlfriend by Facebook, so we were wondering if Facebook can be considered as a publication already to claim some credit, but apparently we decided not. So anyway. So Higgs and quintessence, there are several things. Either you can consider the Higgs as the quintessence field, which is I would say doesn't make more sense, but I think you can explore that option. But then there can be the coupling is such that at the end it is you can separate the coupling, and that's what I think. But Arthur and collaborators say that there's all like a coupling of the. It is separated, but then there has to be some coupling of the Higgs to the quintessence. But then you have to explain in string theory why the quintessence couple onto the Higgs and not to the fields in the standard model and so on. But we explore several ways, if you have several other fields, not only the Higgs and the quintessence, but also extra fields, phi. And then since the conjecture is in grad of the volume, so that you can now explore several directions. And we tried, and essentially, in principle, you can tune things to pick some particular functions that satisfy the criterion, but either you have you will either break the other conjectures, or at the end you have another minimum. So at the end, it didn't work. But I think it was worth exploring how strong this argument about the Higgs, and I think Arthur will mention more in his talk. So that's the sitter versus quintessence. So how to get quintessence from strings? So we say how difficult it is to get the sitter from strings, but we have also to then ask the other question: how difficult will it be to get this quintessence from string theory? It's not only say, well, the sitter is very difficult, then let's assume quintessence is there. Let's see how difficult it is to get quintessence, and that's complicated because if you want to follow all these steps, first of all you need to stabilize all moduli and then let only one field to do the quintessence. Otherwise, you don't stabilize many of them, but then you have to have the quintessence field to be the fastest rolling guy. So it will be very difficult to achieve in string theory. So, and still you have to stabilize many of them. So that's complicated. And then you have to worry about fit force and varying couplings constraints, like was addressed many years ago by Banks et al. In particular, we say that, for instance, the volume model itself is hard for it to be the quintessence field because it couples to everybody. And for instance, you can have the Yukawa couplings for matter fields, and has this dependence on the Kahler potentials that at the end perturbations of that will give you volume dependence of the moduli. And similar for dilaton. However, as Kumrun say, it's not necessarily there can be other moduli, like the ones that I was talking about, the blow-up modes or the fiber model that can be separated from the standard model, and then they can be the quintessence fields. And actually, one of the options using the large volume scenario was explored by Michele Ciccoli et al. In 2012. However, that one required the string scale to be of a TeV, and then you have to add a lot of still some assumptions to make it to work, in particular some cancellations about how to break supersymmetry and so on. Still is an option. My favorite one, I think, is using the Axion as a quintessence fields. There's, as it was mentioned by Matt Cleveland this morning, and so Axions abound in string theory, and they have no problem with the fit force being a pseudoscalar fields, and and actually they have been explored for quintessence in many papers, starting from Ki-Moon Choi in the 90s, and then Panda Trivedi et al., Kahler et al., and Kamyankowski recently, and They assume the simplest case, which is 1 minus cosine, or many of this, but just 1 minus cosine, and they can be simplified if you have several of these fields. And usually you have the problem that f to get to make it to work as inflaton has to be bigger than the M Planck, and the similar thing happens for quintessence. Sorry. And in the large volume, since the volume is exponentially large, the corresponding axion partner will have a mass which goes like e to the minus tau, which is the corresponding modulus, and tau is volume to the 2/3. So the volume is exponentially large, and this mass is e to the minus volume to the 2/3. So a volume of order 10 to the 3 or so required for getting the God scale, that'll give you this mass very, very, very small. It can be as small to be the fuzzy dark matter that Matt mentioned this morning, but it can also be, depending on the coefficients pi over n, it can be also the dark energy. So to get small masses from actions is very, very natural in this scenario. The potentials takes this form as something, it's a small variation from what people have used, but it's very substantial. One is that the potential has the coefficients lambda I times cosine. These lambda i's depend on the exponential of the corresponding modulus field, the partner of the corresponding axiom. But this lambda overall is the one that people use to do the tuning to get the CTR or to get any value. So there is no, thank you, there is no correlation between these two numbers. This can be very small because of that coefficient, but this can be small by some tuning, but the smallness of this is not necessarily related. To get quintessence, you have to have the corresponding epsilon parameter to be smaller than 1, and this is the equation. Since this lambda is different from this lambda i's, the standard requirement that FL has to be bigger than M Planck is not necessary. So, and let me just go to different scenarios. So this is ADS and action, DS and action quintessence. So this is the part when you put the two things together. So there are several scenarios. One is that look at we are fixing in the ultralight actions. So that means that we have integrated out everybody else. All the moduli partners and so on are integrated out because they are very heavy. That's something is also important to emphasize that generically, and I think that fits with Matt's models this morning, the axion and the corresponding modulus partner, they get similar mass because the potential comes from the exponential in the superpotential. However, for the large volume case, the volume gets stabilized by perturbative effects. So the exponential in the superpotential plays no role for stabilizing the volume. So the volume can be relatively heavy, like a TeV or a little bit less. But the corresponding action, as I said before, is extremely light. It's e to the minus the volume. So you can separate the two. So it's not only to get ultra actions. The corresponding partner has to be much heavier than that because if they are both of the same mass, then the partner will create the fit force problems. So this can be realized. So depending on the connection with the lambdas and lambda i's, you can have this possibility. For instance, here the cosine potential. You can tune initial conditions so that you are very close to the maximum. You can get quintessence to work. The minimum can be negative or very negative, for instance. But the important thing is that you are very close to the maximum point, so you tune it so that you are almost at a zero derivative, so the epsilon can be very small. And that could be a possibility to get quintessence. I have to say it's not very natural because the tuning is very high. This is similar to what we had when we had the racetrack inflation, the first model of inflation. In the sense, it was a similar tuning that was required. So this can be done. And notice in this case, we don't need to have a minimum of the sitter. It can be ante the sitter. However, the maximum has to be the sitter. So in that sense, for the conjecture, you have to allow the modified version of the conjecture when the maximums can be the sitter. The other option, which I prefer, which I think is nicer, is what we call quasi-natural quintessence, for lack of a better name. The condition to get quintessence is FL to be lambda L over lambda M Planck. So as I told you, this lambda L and lambda are not necessarily related. So you can just easily have FL to be bigger than that. If naively, people have always considered the two lambdas to be equal. So that was the condition F bigger than M Planck that people have been using as a constraint for quintessence. Now we don't have to satisfy that because lambda L can be much smaller than lambda. Then FL can be bigger than that, but still smaller than M Planck. So that's a possibility. And that's a place where you can have the minimum is the zeta, and the quintessence is still running here. And I say I emphasize here there is not an extra tuning. You select the criticism to get quintessence, and in the landscape, say, because you have to do double tuning, the tuning of the cosmological constant and then tuning of the slope. Here you don't have to do that. It's not necessarily unnatural in the sense that because I told you that this slope depends on the mass of these fields and they are naturally small because it goes like e to the matter volume to the 2/3. So this is a possibility. Again, so that you can have quintessence and the zeta. So that's the diplomatic solution, I would say. And the other one is that oscillating quintessence, the minimum can be very small, and then the field still will be oscillating around its minimum. So it will be dominated mostly by the zeta-like, but still this oscillation that's typical of scalar fields that are displaced from the minimum after inflation. So there will be this oscillation. And then this produces a equation of state which is very different from the standard equation of states. You are sitting in the minimum, that will be W to be equals to -1. Here you are oscillating, the W, the equation of state parameter, is oscillating also, and then that gives you a different picture for the expansion of the universe. So hopefully this can be another option that we can have both the zeta and quintessence, which is different from here. This one is more generic because you can be at any point, say close to the inflection point or so. This one you have to be very close to the minimum and still oscillating. And so conclusions are very simple. The zeta and quintessence are main achievements, challenges, and open questions. And just to say something about when I had the outline said that you may have no de Sitter and non-quintessence, and that's a possibility. People outside our community, they're exploring that possibility, because when we say that W is equal to is very close to -1, actually for many years, the central value has been smaller than -1. So that has been a challenge, smaller than -1. People are now saying it's not only smaller than -1, but it's also oscillating what the equivalent of W can be. So, as Kun was saying, his talk, we have been surprised in the past about low redshift measurements. We may be still surprised. This is only a 2 sigma effect, so we don't have to take it too seriously. But and we have to keep an eye on that, because we have been surprised in the past. And in that case, both de Sitter and quintessence will not work. So we have to be an open mind. Okay. Thank you very much.
So are there any questions? Must be some. Yeah, there. Okay.
So you will have to take into account eventually the SUSY breaking, right? That this may
absolutely
just destroy whatever
yes.
quintessence.
Yeah, that's the good thing about the actions. The actions are okay about SUSY breaking because they're protected by the Pechekin symmetry, so you're okay. It is a problem for using the modulus as a quintessence field, because supersymmetry breaking. Usually, I have to say, thank you for reminding. I have seen in the past several papers using supergravity potentials for quintessence, and I don't find them very convincing, because at the end you have to break supersymmetry, and then the supergravity potentials don't work. You have to use everything with supersymmetry broken. That's the thing that should be, because the energies you're dealing with are much lower compared to the string scale, to the supersymmetry breaking scale. So in that sense, supersymmetry should not be playing that much of a role in this describing the potential. But yes, so in that case, that's what makes that model a bit complicated. The one from where the fiber models were the quintessence. For actions, I think it's fine.
Any other questions? If not, then let's thank Fernando again.